شكرا لله. ولماذا أرسلتني؟ أنا ما عجبنيش هذا الصراحة.
Please.
Okay, so thank you. I can't speak to everybody, but thank you for being busy. And sorry for not being there in person. I was seeing some photos earlier today. I'm very jealous. It was very beautiful. So, yeah, so today I'd like to talk a little bit about this question that we've had for now a number of decades regarding how we think the limits of our components for and for sure, everybody has heard of the problem of cosmological tension. And in the talk, I will cover a little bit about what this is, some possible ways forward, and also some new techniques that we're developing in part thanks to the network that we put together for Cosmogrid, actually maybe some more part of this network. And if you are not part of this network, please join us. And it's just over there, you just look up Cosmogrid online, you will find where to join, that's not an email. I'll say some more details about this network. Okay, so to start off with the takeaway message of the conclusion of this. So if we have heard about cosmic tensions, I guess the question we should be asking ourselves is, why does it matter? Why should we care? And also, what is this all about? So, when we talk about cosmic tensions, the biggest tension to do with the value of the constant is. There's a nice quote here where talking about the importance of theory. I mean, I would think of the talk titles, and I can see that there's a lot of theory. So if we are talking about theory, theory is one of the best tests, the end-to-end test of any model. And in particular, our standard cosmological model, or lambda CDM. Now, if we heard about this as a tension possibly between cyclonic profile and particular two measurements, and the CMB, in particular, maybe we heard about it through the Planck tension, the tension Planck. But it's more than that. It's a lot more than that. It's a bigger tension between our local universe, or you can think of it as the inner-distance planet, or this way in the distances as we go up from geometric distances, Shepard, 5.8 supernovae, and really high distance measure as we see as we go along. And the takeaway message is really that we are very far away from these solutions, whatever the word solution may be for you. That there's a slight picture here, showing the mean values with the output. With a very high value in the local universe and a very low value in the early universe. If you are driving a car, you wouldn't get very far on this bridge. But before going into that, so to think a little bit about standard cosmology, to see the context of why core mechanism is so. This is some changes or some outlier results. So as we know, the things we know very well. And if we think about lambda CDM, the base of lambda CDM for us is electricity, where we have derivative to the V by theta connection. We understand the geometry very well, we understand the processing technology, but not very to the Newton direction. Putting macro on top of that, again, regular understanding model physics, which is not is in a number of senses, but it's not complete. And we have also our bedrock of how we build our cosmological model. And sticking with this language of questioning how to improve the universe and also the early. So look at the early universe. And okay, what are the issues? So no, already that we need to add concentration or horizon and problems, that sort of stuff. So there are many ideas. But the downside, there are a number of unresolved issues. For a long time, we've known about ADS or different nuclear synthesis. For a long time, we've known that the prediction of the production of lithium in the early universe doesn't exactly agree with what we see in the earliest part, the oldest part of the universe. So there's a 2 sigma engine over there. And in addition, you can hear this has also sort of polluted our understanding of how helium has come to the universe. This is not the same statistical universe, but this is the question mark. If we look at the legacy science data, we have issues regarding ecologics, but we have hints, let's say, about the flatness of the universe. So artificially, we always said on NRK to the zero and almost all reality. But this is not a theoretical prediction, this is something we set by hand. Also looking at the CMB, looking at large scale hypotheses, which are not in the same, they don't appear the same way, we should have looking purely at lambda CDM and predictions that come out of that. Similarly, in the CMB, there's a particularly strong inverse transpose effect. And recently, then looking at cosmic dipoles, there's been a slight hint about maybe possibly some hints about breaking the cosmological picture. And there are other examples by the same reason CSV. And there's some open questions like the amount of dark matter that we get from CMB. Does that really agree with solar scale dark matter? So really, there are, okay, we can't really wonder that, but there's a lot of questions which require an explanation beyond inflation. The inflation doesn't really either the full cost or nothing else. That's the area of it, where we have, while we have specific cosmology, you have less access to, let's say, the data that we have at late. So in the late universe, by and large, we may have the issues that are here are issues that we had for a long time. So as we know, we have dark matter to the model, which comes with its own ups and downs. So we're looking at cold dark matter, which is our kind of model, traffic problems, or missing satellites, there are many galaxies in our own. Then looking a little bit deeper, so looking at cosmological quantum of dark energy, we know, and so this was discussing having some fundamental understanding beyond cosmological explanation they have in another CDM. Looking at data, in particular from Pantheon studies and other places, there's been a considerable confusion here to look at possible variations of vector parameters, including but many others like omega matter in different directions, for the northern hemisphere and southern hemisphere. And there's been some work on using the diagram study pixel to get an estimate of phase noise, which again comes with this issue. So it's in this context where we have a number of questions and anomalies which are at a statistical level over 2 to 3 6 months. That on top of it, then we have to see this issue of computation, which now in that context feels a little bit more like a final area of if correct, if not explained away by some systematic or magic systematic that has been missing in context and related with these measurements. So in this context, to explain a little bit, I don't know if someone wants to if someone wants to ask questions to speak. And so in this context, if we're looking at the value of x, we're looking at the linked universe, there's the two time over here of roughly 73, 74 with lower uncertainty. With even lower uncertainty, the legacy time value at roughly 60 long-distance equatorial apart. Some differences to mention, in fact, this is maybe one next slide. Some differences to mention is that in the local universe, we have the ability to make these measurements, and of course, not a discrete way. So that was depending on lambda CDM. It doesn't mean so much. We can, so I'm showing this picture here, which appears in the latest, in the bottom of perspective, and which is, I would say, the latest compilation of many estimates of data. And on top, what we're seeing is we're seeing measurements of measurements that come from the early users. But it's important to the same context, where in the top bar, these are mainly CMD measurements, but they also depend on BGL, and I'll say something in the slides about that. But these CMD measurements and even BGL depend on us assuming under CMD. There's no way of going from CMD to H0 since CMD is H0 as a model parameter. In the middle, the largest section, they have these four directions. These are not obviously free of systematics, they depend on physics and our understanding of scenarios. But already even by eye, you can see that there's a general trend between different targets without different measurements. But it is generally a higher value of treatment, which is the thing that we're talking about here. And then at the bottom again, there's larger uncertainty, but here there's a little bit more modeling. So when I say more modeling, not necessarily physics modeling like that at the end, but for instance, the first one is where some elements of the machine is average signal and data and how JavaScript includes it is utilized. But this picture, I think, really visually impresses on us and the gravity of the situation, where we really have a dramatic difference between measurement station year universe assume lambda CDM, measurement station the local universe, which are basically only dependent on physics, by and large. And it's clear that, we're trying to find the solution. Now, I'm just going to talk about some of these measurements. Something really. I'll just talk about two from the early universe and two from the late universe. I know the question for a few years about this being an issue, as I said in the first slide, and between the late universe, the universe and CMD. So it's well, on the next slide, but it's BVN that really resolves this issue. But starting with CMD, so I guess what I'm sure of the line there is survey, and some ordering of that survey where, we're getting the very low value of income, but it's not this alone. So recently, there was also, as you can see, the system of the middle, there was the act release of estimating H naught, and even more recently, this release, which again confirms the very low value of H naught. But this may be something that we know, something maybe to add and add. Again, this question of whether this is a peculiarity of us maybe not understanding what is CND. And it's really big bang influence things are that I would say contentiously resolves the issue or remote inspection. So BGL, though we cannot give us a very strong estimate of those parameters, like case control or the maximum parameter or negative. However, with BAO data, parameter oscillation data, and it's able to give us this as a type. So in the table up here, there's all different data sets related to CDN, but the basic point to take away from this is the founding precision or the consistency, sorry, between these different estimates. So again, we're really at the CMP value over there. Keeping in mind that we're talking about the early data and correlation with the ratios. So from early universe, we're really getting a consistent picture on the lambda here. But what about the opposite side of the coin? Our late universe or local universe. So looking at the shoes release related to this measurement, so just to explain a little bit, so we have a work on this inside into this tree on Hubble diagram. Building from in the first round with geometric distances, then to check by stars, and then finally in the Hubble flow using hyperwave and pressure. But interestingly, on the right hand side over here, you can see a whole series. So this is the world different systematics we're looking at, ranging from metallicity to string of outliers, looking at all the different things that the community has really pointed as possible explanation for why they're getting this very high value of things. I think there's roughly 67 data points here, which again, even just looking by eye, you can see how consistent they are with the reported value of 78, 73, 74 kilometers per second per megaparsec. But this is a lot. This, I guess, is the question. So the Taiwanese supernova, as I was saying just then, depends on building a distance ladder. So we are building our distances depending on different things. Just like stars or everything, and then going to Taiwanese supernova. What about distance ladder screen mechanism? So this is a bit like BBN going to CMP. So over here, we're looking at strong lenses. So this is where you're looking at the quasar or something being lensed by something galaxy. And you're looking at the time delay between the thickness on different sides of this lens. Again, just mentioning what this collaboration here, the Cosmo collaboration, finds the result to give some context and picture to the problem. And again, at the bottom over here, you can see circle, you can see that they don't have many lenses. So there are some with one lens, and there are some with a maximum of 7 lenses, 7 different lenses. Hopefully, with this grid and if it's on a mission, this number will dramatically increase, so they're about 3. But already, again, you can see very big consistency, but they get higher levels. But they are all consistent up to 1.1 with the shoes really over there. So again, so in this context, I think I need to look at things where, okay, there are 2 points here, so I guess the most telling is on the right, where we can see how how early the CMB measurements thing have varied over the last couple of decades, and more the late universe, and how the tension was in a sense always somewhat present, but not really expressed. And only at the end was that we started to have statistical significance in the presence of this tension. And then on the rest of the year, basically on one measurements that we can use where again pretty clear that something is going on, whether I think someone is on my phone. And so whether the systematic, I would say, is becoming more contagious over time. Because the trying to explain how we want to use the incentives for the government. For some who are saying systematic maybe the case, but may more likely be the case, may more likely be the case that there is some some indication of new physics somewhere in this. So this is sort of where we are. This is the cosmology potential problem, let's say. Or this is the hardware tension problem. So looking then maybe at possible solutions. So again, depending on the new white paper, which we just put on the archive months ago now, and was recently accepted by Principal of the University. And as we know, we have many ideas related with music. So there's like top down the left of some of the different ideas that we're looking at, but I guess what's different in what we're sort of talking about here is that we're looking at these different, let's say, models, instead of thinking, okay, we need to think fundamentally about the big model, but also we need to think about the action, the invention of it. What are they doing to our cosmology if we're trying to resolve the hypertension issue? So, okay, so we have the archive which is full of discipline of many time solutions, which are centered in thinking our daytime physics, so using CMB as a lambda PM, but using the late universe, these numbers look like on meaning that we have really quick in data in the late universe, so it's very hard to put dynamics there that isn't excluded by data. So that is the other human being. There's also a lot of work engineering looking at deviations from the cosmological principle. It's not at the point, I think, that we can really say we're building models now. I can't be correct this, but that's where the community used to be in that sector. Modified gravity, which I think is comprehensive, is not much point is talking about, but as we know, we can always change this incentive reduction. And I guess I need to add on the next part, maybe to add the comparison of what's happening is that we have to think when we think about quantifying gravity. And how this may be unique or not to generate with other companies without addition to the standard cosmological model, such as adding new mathematics. Okay, as you know, there's also a lot of work in quantum gravity, but so far I haven't seen many attempts at solutions of any cosmological tension problem. From that, matter solutions, okay, having coupling between different kinds of dark matter and energy, the decay, and dynamics, and other solutions like nuclear void. This is definitely a possibility. There's a lot of work by Leandro, by Osgur, who look at possible, for instance, changes in the cosmological constant, finding the cosmological constant, and so on. And this is also early kind solutions, which are very promising in a certain sense. And it's a bit of a question mark now. But there is a way that you can sort of like hide the new physics beyond recombination. So put this behind the CMB. I'll say a bit more in the later on. And so just going on for to stay on time as much as possible. Okay, here is another slide on the number of theory. It's the same thing, it's just a different way of looking at these different modifications. But again, to try and stick with the time. So one other interesting way to look at these new kinds of solutions, again, I can give a survey, quick survey of some interest in the literature relating to the tensor solution. So before I was showing different ways of building one, what about different ways of expecting? So one nice project that there was in the last few years was something called the Higgs Olympics this year. So the goal here was to take models that had public voting proposals which are available online that can be used to basically run science to run some of these type 1A supernova data sets like Amazon Plus, and to look how that relates with the estimates of counting plans, the counting shoes that I mentioned earlier, and other things like biometric BGL data. And okay, you can see the measures here and the different models. So here, there's to mention a few. There's a lot of EGE and NCEE. So these are related to these early times. But it turns out that the best model that comes out of this is actually having a varying electron. You can say maybe physical or physical, but statistically that turns out to be the best model here. And also having some to give an allowance that has the certain parameter varying more than the parameter sorry, not varying, being zero, or only makes this fit even better. So this is food for thought, I would say, food for thought. But I think it really compels us to not just think about model development, which again I think that there's a length here, but to also consider getting this really to the point that this can be practical. So when I say that, what I mean developing cosmology proposal goals, really confronting data in this way. And so, the cosmology my data. Another, so there we're showing what this consolidate paper was all about. In this very recent data that they had, we also did something similar, maybe in a different, with a different statistical treatment. Since we had many more contributors and many more models to consider, to think about. And here again, not to go through everything, but here, again, it's just showing, and I think the series of the fact of where we are. So each one of these points is, or almost each one of these points is a unique model. There's a lot of results carried into this energy, but by and large, these are all different models. And we can see really the spectrum of values of each model we're getting out of these different models. So I think this comes back to that question, that point that I mentioned earlier about the generator. When we're thinking either about modifying narrative or modifying whatever we're modifying, that we really need to think in the community. And this is like an open point for the conversation about the generosity between suggestions of having more and more exotic physics and what the impact of that is. Okay, we need to have this, we need to retain what goes in standard model. But we need to think also the impact of having these exotic terms. But anyway, so we've really developed, I think, so far the language of early versus late or local measurements, or developing models are thinking about the effect of either early universe and local universe physics. And coming back to this, building up essentially to really dark energy. So when we look at the CMB, there are a few things we're looking at. We're looking at measurables and things related to measurables. And when we're looking at the different temperatures, the different hot and cold spots in the universe, and what we're really looking at is other things that give us large the things that give us like barrier and these are related to what's called the sound horizon, which is the distance that diagonal, so this is why that opens and in reality to move in the universe, and given the expansion of the universe as we constellation. And the thing that we're looking at here is the angular size of the sound horizon, this is what we can take away when we're looking at measurements of CMB, and the angular size of the sound horizon. So this is the sound horizon of how far away is that could these diagrams move to have the same deficit in a sense. So looking at this back of the envelope calculation over here, theta s, the sound horizon, is basically the product of the radius of the sound horizon and theta. So what can we do? We can decrease the sound horizon so that we can increase the value of theta. At least at this level, it's been better. And that would be changing early university. On the other hand, the other way that we can approach it is to think about changing the religion. Now, the universe, again, I can't emphasize this enough. There are many aspects behind changing the religion, but we really have a lot of data, with lots of very strong deep into high-risk state, which really limits what we can do. It doesn't mean that we don't have solutions there, we have data on this solutions that we can have. But it goes into question how exotic do you want it to be. Before I mentioned this idea of graduated energy, where we have a cosmological constant, which spontaneously or almost spontaneously changes time. And then we have a world model related with interacting, dark matter, dark energy, decay, dark matter, dark energy, exchanges, couplings, that sort of stuff. Then in the last one over here, we also have this idea of having a running factor model. So the changes the cosmological constant. And there's a lot more to this. There's also a whole quantum model, quantum gravity model behind it. So I'm just talking about this in the context of things. And so that's what we can do later. To come back to this idea of keeping our angular scale of the sound direction fixed and reducing the sound horizon and the universe effectively just means having a faster expanding universe in the previous combination here. This gives us a way to boost the value of X. So this is where you have a larger value of X. So this means that the users are full faster and the users think that sound is fine because of two resistances. So there's a lot of impact going on over here. So the effect of this in physics would be, in a sense, I don't use the word physics, but it's like a physics beyond recombination in that sense. So it's not something that we would see like the effect of dark energy in the universe. And the most promising, let's say, idea of having this effect would be through something called early dark energy, where there is a little complicated field, and there are some details here, but I think looking at the graph, we can see the density parameters of at least at the bottom, we can see the density parameter of early dark energy. We can see that if we have AMD at roughly 10 magnitude, that's roughly 1,100 vectors. But this speaks really beyond that. This speaks really beyond that. And so it's effectively beyond that. And then we still have the regular cosmology that comes after that. And as we know, the universe and diagonal away. The only issue is that as we look at these different models, so here is the number. And looking, I think, just speed up a little bit, if we just look at this middle plot right here, they do push the value away from the Dirac band, but it doesn't quite get to the shooting value. So EBE seems together close there, but not exactly there. In fact, I'm going to skip this slide, guys, this time. And the reason is very simple. So if you have a user to expand faster, it means that you have less structure formation. So the BAO basically biometric information is going to be in less than the record. That's what the graph on the left is showing us. So very basic level, and it means that if I have a faster expanding universe, I'm going to have less time for structure formation, which ties in with another important tension related with SAE. So recently, this question may have actually gone over with the latest release of theory and the collaboration. But it may focus us, let's say, in the whole time. Again, SAE being a metric of larger structure formation. This is also true with the legacy results, and again, we released 3 months ago. And then again, over here, I always this is at a much weaker statistical tension. But again, the tension in large structure formation is something that is not really present. And okay, like before there are related to the white paper, but I want to talk about on final thing before finishing. And I'm going to skip part of that. I thought I would go faster, but anyway. So just to mention some other parts related with what movement, the second sex rate. And okay, so I mentioned one of the model six, which are related with regular marketing on Carlo and PhD and using both and solvers. But beyond that, there's a whole bunch of new techniques which are being developed. These are not at the right level of maturity right now to be competitive, but they are very, very close. They are not far away. So this involves things like reconstruction, but also things like replacing the sampling in marketing on the groundwork, and other things like model services. Give one simple example. So there's something called Gaussian processes, which is if you set a way to look at certain data sets and to interpolate and extrapolate that data in a statistically meaningful way, providing Gaussian data, as the name would imply, and using just statistical models. So we're not model free, but we are depending on regular statistics rather than depending on physics, to make it that way. And the idea is to take data points and try and find relationships between these data points. We do that with what's called the covariance function or kernel and many things. This is the Gaussian kernel, so one of many. And to show you an example of diagram, the fact is, okay, there's a dollar sign now, but if I take a number of different data sets of positive parameters, isolate supernova and diametric oscillation data, I take all of these data points. I can use Gaussian processes. So not just interpolate the depth